All right, so today we are going to be talking about electrostatic actuation. So electrostatic actuation, um, it's a way to induce motion in a microstructure by utilizing the attractive forces that occur whenever you have a separation of positive and negative charge. So let's consider a simple parallel plate capacitor. Okay, so let's say up here we have our top electrode, and we are going to allow our top electrode to move. And I'm just establishing the coordinate system here. So this is going to be our X direction. And down here, we have our stationary or anchored electrode. And let's say that there is some suspension represented by Km. So that's going to be our mechanical spring constant that allows our movable electrode to move with respect to our anchored electrode. And our initial condition on our system is going to be that we have a bias voltage of 0 volts. And in this condition, our plates are separated by some finite amount, D. Okay. Well, what happens if we were to apply a bias voltage across our plates? So I'm going to draw another little picture here. Okay. So we have our top electrode and our, which is movable, and our bottom electrode. Now our bias voltage is non-zero. Sorry, you guys are hearing my dog's collar jingle as he is going crazy to get let outside by my wife. So we have some non-zero bias voltage that is applied. We're going to find out a little bit later on that the polarity of it doesn't matter. We're still going to have our suspension Km here, but we should observe that the new distance between our plates is going to be given by D minus X, where X is the movable electrode displacement caused by the application of our bias voltage. So effectively, if we apply a low frequency voltage across our capacitor electrodes, and one of the electrodes is allowed to move, Coulombic attraction between the charged electrodes is going to generate an electrostatic force, Fe, which will cause the movable electrode to displace towards the anchored electrode. So I'm going to represent my electrostatic force Fe as a force in the down direction, like so. And we're going to throw a little math at this. Okay. So the movable electrode's displacement causes our capacitance C to vary as a function of that displacement X, which can be represented as C will be equal to epsilon, our permittivity, multiplied by A, our plate area, divided by D minus X, which is the distance between the plates under bias, right? So this is nothing more than our simple parallel plate capacitor equation, okay? Now, we know that the energy stored by a capacitor is dependent on the capacitance value. And since our capacitance value in this case is dependent on X because we're allowing one of our plates to move, that means our energy is also going to be dependent on position. So we're going to have 1/2 C of X times our applied voltage V bias squared. And doing simple substitution here, this is going to look like 1/2 epsilon A over V minus X times our bias voltage squared. And finally, since we know that force is simply the derivative of energy or work, our electrostatic force will also depend on the value of the plate displacement X. So we're going to have the derivative of energy with respect to position will be equal to 1/2 times the derivative of the capacitance with respect to position times our bias voltage squared will give us 1/2 epsilon A over D minus X squared times V bias squared. So we can make a couple of observations from this equation, okay? So the first observation is that the electrostatic force Fe will always be in the direction of increasing capacitance. So the Coulombic attraction is always going to try to pull the plates closer together to each other. And our second observation is that the polarity of the applied voltage really doesn't matter. So because our force is dependent on the excuse me, because our force is dependent on the square of the voltage, the sign of the voltage is inconsequential with regards to its ability to generate a force. Okay. So in our system here, our electrostatic force is countered by a restorative spring force, Fm. So effectively, if we compress that suspension by applying a voltage, the suspension or the spring is going to want to expand back to its rest state, okay? So we have forces acting in opposite directions. The total force acting on our system, F total, is simply the sum of our electrostatic force. So that's the voltage trying to compress the plates together, plus our mechanical force or our spring force trying to keep the plates apart. So this is going to look like 1/2 epsilon A over d minus x quantity squared times our bias voltage squared minus km times x, where that minus sign comes from the fact that the forces are acting in opposite directions. And I'm assuming the x direction as downwards, so that positive x means the plates are moving closer together. So this is a very interesting result, because our restorative spring force, Km of x, depends linearly on our plate displacement x, whereas our electrostatic force depends on the square of our displacement x. So what that means is that at a sufficiently large displacement, our electrostatic force will actually be larger than our restorative spring force. So when this occurs, our plates will simply snap together because our restorative spring force is no longer able to counteract our attractive electrostatic force. This phenomenon of the plates snapping together beyond a certain displacement is what's called the pull-in effect. Excuse me. So the pull-in effect in some applications can be a good thing. The pull-in effect is used extensively in the operation of MEMS capacitive switches. And effectively, the pull-in effect allows us to actuate those switches, so close the contacts by applying a pretty reasonable bias voltage to cause it to occur, because we're effectively exploiting the system's instability in order to do so. And then we actually in turn get to use an even smaller hold down voltage to keep the switch actuated. But for a lot of applications, like tunable capacitors for RF applications, the pull-in effect is generally something that we want to avoid, because when the plates snap together, the capacitance is no longer tunable. It is just a fixed thing. Actually, it's not even a capacitance anymore because the plates short each other out. Okay, so we are going to analyze the pull-in effect and figure out mathematically when it's going to happen. Okay. We're going to do this by treating the pull-in effect as an electrostatic spring force. So our total spring constant for our system is going to be the derivative of our total force as a function of position taken with respect to position. And in carrying out this derivative, we wind up getting epsilon A over quantity d minus x cubed times our bias voltage squared minus Km, where this is simply our electrostatic force, Ke, electrostatic spring constant, Ke, minus our mechanical spring constant, Km. So we're going to define our pull-in point as the point at which our electrostatic and mechanical spring forces completely cancel each other out. So effectively our total spring constant will be 0. So or our total force will be 0, would be a better way to put it. So if we say that 1/2 epsilon A over d minus x squared times V bias minus kmx is equal to 0. So this will be true. You write that. True at pull-in point. Then we can rearrange this expression and find that our bias voltage squared, will be equal to twice km x times d minus x squared over epsilon A, nothing more than simple algebraic rearrangement of this equation. And if we substitute in that relationship for V bias squared into our spring constant relationship or our stiffness relationship, we get K total will be epsilon A over d minus x cubed multiplied by twice km x d minus x squared all over epsilon A, and epsilon A cancels out epsilon A here. D minus x squared cancels out 2 powers down here. And what we're left with, minus km, I forgot that bit. So what we wind up being left with is 2 kmx over d minus x minus km. So what I'm going to do over here on the right hand side is effectively just plot this relationship. So we're going to have x over d as a ratio on our x-axis and our total spring constant over our mechanical spring constant as a ratio on the y-axis. Start at 0. Etc. And then on our vertical axis, we're going to have -1, 0, 1, 2, 3, 4, 5, 6, and so forth. And so it's red. Curve is going to look something like this. These guys cancel out here at this point. So when our displacement is less than effectively d over 3, our mechanical spring is able to counteract the pull-in effect of our applied voltage. At exactly d over 3, the mechanical spring force and the electrical spring force cancel each other out. And then for any displacement greater than d over 3, our electrostatic spring force is overpowering our mechanical spring force. meaning that a very, very small change in voltage, applied bias voltage, will cause a very large change in our plate displacement. So we've hit a point of effectively positive feedback, or at the very least, system instability. So X is equal to D over 3 is the pull-in point of our system. Anytime our displacement is greater than that, or we should actually expect that our plates will simply just snap together. So using this as our reference point, we can now calculate what voltage will cause pull-in. Okay. So our pull-in voltage, VP, is going to be, so let me scroll back here just so I show you what I'm using. So I'm going to use this equation right here, except I'm going to substitute in D over 3 for the quantity X. That will allow us to calculate our pull-in point, or pull-in voltage, excuse me. So I'm going to have 2 km times X, which in this case is D over 3, times D minus D over 3 quantity squared, all over epsilon A. Well, this is the same as 2 km times D over 3. And then D minus D over 3 is simply 2D over 3 quantity squared over epsilon A. And now we're just doing a bunch of simplifications here. So 2D quantity squared is going to look like 4D squared. When I multiply that by another D, I'm going to have 4D cubed. 4D cubed times 2 km is going to look like 8 km D cubed. And then I have 1/3 times 1/3 times 1/3, which looks like 1/27. So I'm going to have this over 27 epsilon A. And I'm going to rewrite this very slightly now. So I'm going to call this 8 km D squared over 27 C naught, where C naught is the unbiased capacitance of our system, excuse me. I need just a moment to go get a lozenge. All right, so from here, we can determine our pull-in voltage simply by taking the square root of this expression. So our pull-in voltage, VP, will be the square root of 8 km D squared over 27 C naught. So I'm going to pull out a factor of 2 for my square root sign. And a D. So that's going to leave me with a 2 km here. I'm going to pull out a factor of 3 for my denominator. That's going to leave me with a 3 C naught here. And then I could rewrite this as 2D over 3 times the square root of km over 1.5 C naught. So all right, so what we're going to do now is we're going to work a couple of example problems if I can catch my breath. So let's start with one that's fairly straightforward. So I'm going to draw a microstructure here, and this is pretty much the first MEMS variable capacitor that was developed. It was developed in around 1991. And it was a pretty simple structure in which we have a plate like so. And it is suspended above our substrate by 4 guided beam springs. Springs were curved like this. Sorry. We have anchors like so. And do this in gray. So this is our electrical connection to our top electrode. And then our bottom electrode was literally patterned underneath like so. And so we have a simple parallel plate capacitor where our top plate is allowed to displace really into the page only, like it would be free to move out of the page, except that when we apply a voltage, it's going to try to draw the plates closer together. Okay. The design had an area of 500 microns times 500 microns for our plate area. The nominal gap was designed to be close to 1 micron. Here. And the spring constant of the 4 guided beam springs connected in parallel was approximately 20 newtons per meter. So what I want us to figure out is the tuning voltage range. So effectively, what bias voltages can be applied to this thing before the pull-in effect causes it to no longer function as a capacitor. And the capacitive tuning range of the system. So effectively, what are the endpoints of the capacitance at unbiased and then biased on the edge of pull-in. So our voltage tuning range, or tuning voltage range, however I have it written here, is really just going to be from 0 to our pull-in voltage. That's our theoretical limit. In practice, we wouldn't get close to our pull-in voltage because we don't know for sure that our gap is exactly 1 micron or that our area is exactly 500 microns squared by 500 microns squared. So our theoretical limit will be from 0 to VP. Since VP depends on C naught, we're going to need to calculate that first. So C naught in this case is simply going to be epsilon A over D, assuming that there's just an air gap between our plates, which was true for this first design. That would be 8.854 times 10 to the minus 12 farads per meters times 500 times 10 to the minus 6 meters, quantity squared, divided by 1 times 10 to the minus 6 meters. And this gives us a nominal capacitance of 2.214 picofarads. Using this value for C naught and our other design parameters, we can see that our pull-in voltage, VP, 2D over 3 times the square root of Km over 1.5 C naught is going to give us 2 times 1 times 10 to the minus 6 meters over 3 times the square root of 22 newtons per meter over 1.5 times 2.214 picofarads. And excuse me, this gives us a value of 1.716 volts. So our voltage tuning range is from 0 less than V bias less than 1.716 volts. Any voltage greater than 1.716 volts causes our plates to snap together, thereby shorting out our capacitor. We can determine our maximum, or excuse me, our capacitive tuning range now as well, or at least our theoretical maximum. So we know that the capacitance will be at its maximum when the plate displacement is exactly D over 3. So at the edge of pull-in. So our maximum capacitance is going to be epsilon A divided by D minus D over 3, or epsilon A over 2/3 D. That's going to look like 8.854 times 10 to the minus 12 farads per meters times 500 times 10 to the minus 6 meters, quantity squared, times 2/3 1 times 10 to the minus 6 meters. Excuse me. We get 3.320 picofarads. Okay. So our capacitive tuning range is from 2.2 picofarads will be less than CW, which I'm just calling that a work capacitance, or variable capacitance will be less than 3.3 picofarads. So effectively, this device had a tuning range, or a theoretical tuning range maximum of 50%. So the maximum capacitance would be 1.5 times the nominal capacitance. It's actually true of any design like this. You can easily mathematically prove it. But in practice, the researchers that developed this device were able to only get an 11% capacitive tuning range. So an increase in capacitance of 11%. And the reason for this is because their plate deformed under the applied bias voltage. So we are making the assumption here that the plate is fully rigid, but that won't necessarily be true. We have to make sure that our plate, if we were to design something like this, was thick enough to be rigid when this electrostatic force is acting on it. There were several iterations on this design that tried to extend the capacitive tuning range, right? So fundamentally, it was limited to 50% before the pull-in effect happened. So they did things like put in insulating microstructures in between the plates so that when pull-in happened, your plate would hit that insulating structure and then would bend, giving you a greater tuning range. But the cost of doing things like that, the cost of processing and the time it took to do it, were far too expensive to make it of any practical use. We'll talk about other ways that people tried to get around these tuning ratio problems and all that kind of stuff a bit later when we talk about membranes and things like that. So I want to work one more example problem. So we have a similar situation. We have a plate mounted to MEMS springs. In this case, we have one spring here. And then another spring oriented like so. We're going to call this distance LGB because we have a guided beam spring. Both of the guided beam springs have the same length. This distance will be WGB. Both guided beam springs have the same width. And then there's also a thickness oriented into the page. So we're going to have LGB is equal to 400 microns. WGB will be 10 microns. And TGB will be 1 micron. Then we have a plate length, plate width, and also a plate thickness. And let's say that our structure is made of polycrystalline silicon. So it has a Young's modulus of, 120 gigapascals. Can't write today. and the designed gap between the plates is 2 microns. We want to determine the vertical displacement of the top plate for bias voltages of 0.4 volts and 0.2 volts. All right. So let me scroll back here so we can identify effectively the equations that we're going to use. So this guy right here relates our bias voltage to our plate displacement X in terms of quantities that we either know or know how to calculate. So this is the one that we are going to use and rearrange here, okay? So one of the first things that we're going to need to figure out is our mechanical spring constant of our system. Okay. So for one of our guided beam springs, our spring constant is 12 EI, where I is the second moment of inertia times the length of our guided beam spring cubed. Since we are assuming bending in the thickness direction, I is going to be W times thickness cubed over 12. And so the 12s are going to wind up canceling each other out. And so we're going to be left with E WGB TGB cubed over LGB cubed. And I'm running out of steam here, so I'm just going to give you guys the number. Comes out to be 18.75 millinewtons per meter. So we have very soft springs, which makes sense when their thickness is only 1 micron, but their width is 10. So they're very easy to bend in the thickness direction. Because we have 2 of those springs connected in parallel between our mass or plate in the middle and in our anchors, our mechanical spring constant for our system is going to be just twice the spring constant of one of the guided beam springs, which comes out to be 37.5 millinewtons per meter. So now we're going to calculate a couple of other things here. We're going to calculate our pull-in voltage because we effectively need to check whether or not we are exceeding it with either of our bias voltages as well. So much like in the last example problem, in order for us to calculate our pull-in voltage, we need to calculate our nominal capacitance for our device. So in this case, C naught epsilon A over D, plugging in, actually, so this will be epsilon LP WP, excuse me, over D. We get 7.083 times 10 to the negative 13 farads. about 0.7 picofarads. A little smaller than our last example because the plates are slightly smaller and the distance between the plates is twice as large. So that seems like a reasonable thing there. And from here, our pull-in voltage, 2D over 3 times the square root of Km times 1.5 C naught, plugging in our results from previous steps. Our pull-in voltage in this case is 250.492 millivolts. So those very soft mechanical springs means that it only takes a very small voltage in order to cause the pull-in effect. So our first bias condition that we were checking out is 0.4 volts. Since 0.4 volts is greater than our pull-in voltage, then quite obviously, our plates have experienced the full displacement of 2 microns, right? So if V bias 0.4 volts is greater than VP, or not even if, because our plate displacement X will be equal to the entire gap of 2 microns, and our variable capacitor is no longer working as a variable capacitor because the plates have shorted each other out. Okay. Now, for our 0.2 volt bias voltage, that's obviously under or less than our pull-in voltage. So we should still have variable capacitor performance. So if I look at my expression, V bias squared will be equal to twice Km X times D minus X squared divided by epsilon A. I can rearrange this, right? So if I effectively expand everything out, what I'm going to wind up having is x cubed minus 2x squared d plus x times d squared minus epsilon A times V bias squared divided by, when's my stylus stop working? Twice Km will be equal to 0. Okay. So we have a third order polynomial. So I used MathCAD to solve this. Since it's a third order polynomial, there are obviously 3 solutions. So our first solution, which I'm going to call x1, was 0.245 microns. Our second solution, x2, was 1.210 microns. And our third solution, x3, was 2.545 microns. So I'm going to put it up to you guys to tell me which one of these is correct. So which one of these is the actual displacement for the 0.2 volt bias voltage? Anybody have any thoughts? So Mr. Gordon says it cannot be solution number 3 because X3 is greater than our nominal gap of 2 microns. So that's absolutely correct. That is one very easy one to eliminate, right? Since X3 is greater than D, that would imply that somehow our top plate got below our bottom plate, which is physically impossible. So that's a good one to eliminate. So our choices are down to 2. So using a similar line of reasoning, our displacement can't be greater than D over 3 as well, right? Because if our displacement is greater than D over 3, we're at a point where our plates will snap together due to the pull-in effect. So for this particular instance, D over 3 would be 2 microns times 1/3, or 0.667 microns. So that means X2 can't be a solution either, right? So the only solution that meets the criterion that we have a reasonable displacement without the pull-in effect taking over is this guy X1 of 0.245 microns. So if I were to give you guys a question like this on your homework, things like that, hopefully you would be able to figure out what is the correct solution out of the 3 different things that you're going to be dealing with. All right. So I am pretty well gassed. So this is all that I'm going to talk about for today. I'm not allowed to return to campus until next Tuesday at the earliest. Because it's a 5-day quarantine period for people that test positive for COVID. So class on Monday will also be over Zoom. Since I can't be on campus on Monday, we also can't have our test on Monday either. So we're going to push that back until Wednesday. So I will get off my butt and upload the study guide later on today. Probably going to take a little bit of a rest before I do that, but I will get it up today. And then you guys can use the weekend and all the way up until Wednesday to study for your exam. If you have any questions about anything, by all means, feel free to email me over the weekend. I'll be around my computer as I'm working on things, trying to catch up and all that kind of jazz. So I will see you on Zoom on Monday, and hopefully most of you face-to-face on Wednesday.